So let's look at a bunch of cases the way we saw for k-nearest neighbor and naive Bayes. So first things first, what is the decision surface? The decision surface we have for logistic regression is a linear decision surface, or you can call it a hyperplane, right? Because what do we have? We have a hyperplane that separates all the positive points from negative points. So the basic assumption that logistic regression is making is that your data is linearly separable, or it is almost linearly separable, What does linearly separable means? That given your features, all of your positive points, all of your negative points are on one side, right? And all of your positive points are on the other side. That's what linear separability means. Linear separability basically means there exists a hyperplane because hyperplane is like a linear surface, right? It's a straight line. So surfaces like circles, or any other complex surfaces like parabolas, they're called nonlinear surfaces or quadratic surfaces, right? And this is called a linear surface. So the assumption that is underlying logistic regression is that your data is linearly separable or almost linearly separable. Almost linearly separable basically means there might be one odd point here that may not be perfect, that may not be perfectly separable. For example, there is a blue point here and there is a red point there. Almost linearly separable means that most points can be separable. There might be some errors in separation, right? That's a fundamental assumption that logistic regression is making for all of its workings, right? The next thing is, of course, how do we do feature importance? and interpretability? We saw this, and interpretability. Model interpretability. We saw this in one of the feature videos that we can use the absolute value of Wj for feature importance if features are not collinear. If features are not multicollinear, right? Of course, if they're collinear, our only option would be to use a forward selection method or something like that. And interpretability is also very good because I can take the most important features and say, given an XQ, I'm giving a class label of +1 because for the features which are most important, right, I can just use the top 5 features or top 10 features and give an explanation on why I gave a positive class label or a negative class label, right? So the next important thing is, what do we do when we have imbalanced data? Just like other techniques, we use we either do upsampling or downsampling. This is a standard technique that we saw in one of our earlier chapters, and we employ the same method even in logistic regression, right? The next question is, what happens to outliers? How much impact would logistic regression have because of outliers? First thing is, logistic regression has less impact. It has less impact due to outliers because of your sigmoid function, right? Remember, I showed you the diagram earlier in the chapter where I showed that one outlier could skew the whole thing if I was not applying the sigmoid function. So the impact of outliers is less because of sigmoid function, but it's not completely avoided, right? So one thing that people do is, people take the whole training data, and they compute a W star by solving the optimization problem. Once they get a W star, for every point xi, they can compute a W star transpose xi, which will give us the distance from my plane pi to the point xi. Now what I'll do here is, I'll take those points, I will remove points which are very far away from my hyperplane, from dtrain. And after removing them, let's assume I get a data set which is dtrain dash. Now what I'll do is, now I'll train it on dtrain dash. And I'll get a W star tilde, the new W star, which is what I'll take it as a final solution, right? So this is a hack that sometimes works actually. What are we doing here? We are taking the whole training data to compute a hyperplane, or to compute the normal to the hyperplane. Then, right? So now once I got my hyperplane, Once I got my hyperplane, points which are very far away, right? Either positive points or negative points, which are very, very far away, right? Points which are very, very far away, like even this side or this side, they're positive or negative points. If most of my points are in this region, let's say most of my points are in this region, points which are very far away, I can find this distance, right, from the hyperplane by just computing W transpose Xi. I will just remove these points from my training data and I'll keep only the rest of the points and recompute my hyperplane. Now my hyperplane will change slightly because these points would have pulled the hyperplane towards them slightly, right? Now when I remove them, my hyperplane will slightly adjust and I'll get a better hyperplane, which is what I'll call it as my final solution. This is one way of handling outliers in logistic regression. But of course, remember, the impact of outliers is less because of the sigmoid function. Now the next thing is, what do we do when we have missing values? Right? When we have missing values, what do? We do the standard imputation techniques that we saw, right? We learned a bunch of imputation techniques, right? Mean imputation, median imputation, or model-based imputation using k-nearest neighbor and things like that. We'll employ the same techniques here. Nothing changes much. The next thing is, everything that we have seen is basically a two-class setting. Is there a multi-class extension to logistic regression? Typically, for multi-class settings, people typically do one versus rest. We saw this scheme earlier. This is something that people typically employ. But of course, there are extensions. Remember, there are extensions. There are extensions to logistic regression. They're often referred to as maxent models or maximum entropy models. There are multiple names to that. It's all the same thing. In some textbooks and literature, they're called maximum entropy models, especially the probabilistic standpoint. The others call them softmax. Others call them softmax classifiers. There is another name which is called multinomial logistic regression. They all mean the same thing. And we will learn softmax classifier when we learn deep learning. When we learn deep learning, we'll look at softmax classifier later after a few chapters in this course, right? So typically, but in general, people typically do one versus rest. But there are extensions to logistic regression using the probabilistic interpretation of things, wherein you can, it's basically a simple extensions to logistic regression. And we'll learn one such extension when we learn deep learning. The next question is, what if I'm given a similarity matrix? Instead of giving each of my points individually, what if I'm given a similarity matrix, right? Or a distance matrix? Does logistic regression work? There is actually an extension. There is actually an extension to logistic regression called kernel logistic regression. That will take similarity matrices into account. So the regular logistic regression cannot take similarity matrix into consideration. Especially if you're given a similarity matrix, regular logistic regression cannot work. But there is a modification to logistic regression called kernel logistic regression. And we'll learn what is a kernel when we learn support vector machines. Right? For those of you who are interested, you can go ahead and pursue some of the ideas in kernel logistic regression. It's a very high-end risk. It's a very, very interesting research paper to read, not very often found in practice. But it works. Let me tell you that it certainly works. Right? So what are the best and worst cases? What are the best and worst cases for logistic regression? Logistic regression best case is if your data is almost linearly separable, right? And if you have a low latency requirement, logistic regression is very good, especially given your L1 regularizer, right? And it's very, very fast to train also. Even the training is just order of day. It's very fast to train. I've seen in my own experience, people, even my own teams, we have trained on billions of data points. It's very, very easy to train logistic regression on billions of data points. Right? The worst cases, of course, if your data is not linearly separable, logistic regression will not work very well. The next thing is, what happens if you have large dimensionality? If your D is very large, what do you do? If your D is large, logistic regression is fairly good, right? Because if your D is large, your data is lying in a very high dimensional space, which means the chance that your data is linearly separable is also high. Because the data is in a very high dimensional space, there are many more hyperplanes that it can choose from. because of the curse of dimensionality, right? Especially if your data is large, logistic regression works fairly well because the chance or the probability that your data is linearly separable is high. But if you want a low latency system, especially when D is large, we always have the L1 regularizer to our rescue, right? So it's very easy. So large D works very well. I've seen cases with even 1,000 dimensions or even more dimensions in some case where logistic regression works like a charm.